Welcome to CS3510. This is I think 16, no 15, 16, someone check. 15, 15A. The topic is linear programming. So we're in the part of the course where we've covered the bread and butter techniques, and now we're on to extremal cases, in the sense that, not that they are rare and they never happen, but the kind of thing that you can only learn from theory and not in practice necessarily. Large classes of problems, you have to know what other people did, tried and failed at to know what can be done. Linear programming is kind of a theory of optimization. It's basically like a framework in which a lot of problems, not every problem, but a lot of problems can kind of look like a linear program. And then if you know it looks like a linear program, you just go Google like linear program solution finder, and then you plug and chug. And that's sort of the part of the moral in it. If you're in ISYE, and I don't think anyone ever is, whoever takes this course, you can take several courses on just linear programming. You can spend your entire career on just studying linear programming. I think I had to take an ISYE course, and we just did linear programming the entire course. So you could spend a lifetime on something that sounds pretty niche. But let's give an example of a linear program. What does that even mean? Where's the word linear coming from? Why is it called programming, etc.? So let's suppose that you are like a businessman, and you have a factory that could produce items up to certain conditions, right? So let's say you want to produce items 1 and 2. Okay, but there are certain restrictions that can be made. First off, you can only make 400 a day of items 1 and 2. It's also the case that you can only make, what did I say? At most, 200 of 1 and 300 of 2, right? Now, you want to figure out which combinations of items 1 and 2 will make you the most money. Item 1 sells for, I think I said $2. But item 2 sells for $5. So you're given a word problem like this, and every word problem like this is, in fact, a linear program. And the definition of a linear program is, in fact, instantiated from a word problem like this. It's a very practical problem. You want to figure out the maximum amount of money you could make. A naive thing to do would say, all right, I can sell item 2 for $500. No, I can sell, item 2 sells for more than item 1. So let me just make as many item 2s as I can. Whatever's left over, maybe I make item 1s. But when you get into the case where there's more than 2 items to sell, it can get kind of confusing. Maybe it's the case that making one item uses a resource and prevents you from selling another item. Things like this can happen. So the only simple part about such a problem like this is the fact that every relation is really simple. So, linear. So in fact, we seek to maximize a cost function, which we'll call it max of some product that we wish to earn, right? So the maximum we can earn is a function of 2 variables. If we had x1 for the number of items 1 we make and x2 for the number of items 2 that we make, what would the function we wish to maximize be? Yeah. Where x1 and x2 represent the number of items 1 and items 2 that we make. That's the amount of profit we can earn. We seek to maximize that. But we are subject to certain conditions, first of which is that we can only make at most 100 of item 1. So we know that x1 must be less than or equal to 200. And we know that x2 must be less than or equal to 300. We also know that we cannot make more than 400 a day. So we know that x1 plus x2 must be less than or equal to 400. Kind of trivially, we know that we can't make negative items. So we can just condition on the fact that x1 must be greater than or equal to 0, and x2 must be greater than or equal to 0. These constraints are usually implicit and not important enough. So we just kind of like always assume that to be the case. So this is an example of a linear program. Why? You have a set of linear equations, and that's it. So that's what a linear program is. Of course, though, there's a whole class you took with the word linear in it called linear algebra. So let's not think about these equations anymore. Let's think about vectors matrices and all that stuff. So let me rewrite this specific linear program in a more traditional linear algebra form. But before we do that, any questions on this set of constraints? Convince yourself you could solve if you find a solution to the set of constraints, that maps to a number of items you can make and then a certain profit. And therefore, the maximum you could do would be, subject to these constraints, the max you could earn would be a solution here. A linear program is simply the set of constraints, right? So what we may say is that we have if you notice here that we have really some coefficients and some constants on the right-hand side and then some constants in this objective function. So what we may say is that we have a matrix and two vectors where B is going to be a m by 1, C is an n by 1, and A is an m by n, right? And we wish to find where each of these encode, for example, A encodes the coefficients on the left-hand side. So A, for example, would be 1, 0, 0, 1, 1, 1. And then B would be, this would be A. B could be 200, 300, 400. And then C would be 2, 5. The standard form for any linear program is you want to maximize CTX, the transpose of C, times some vector x, subject to AX is less than or equal to B, and x is greater than or equal to 0. And again, when we write this, it's understood this is a vector, and then component-wise, each entry is greater than or equal to 0. This is the product of a vector and a matrix is less than or equal to B, right? Convince yourself this is identical to this. These are the same thing, right? This is just a different way to represent it. And we won't concern ourselves. Every linear program looks like this. Maximize an objective function, which is just linear coefficients, whatever those happen to be. The CT just means that you're writing it, it's not up and down like this, it's left to right. That's all that really means. Subject to a set of constraints, specifically linear constraints. Notice there's no square roots in here, there's no squares, there's no logs. None of these functions are allowed to be anything that's not linear. We'll talk about that a little bit later today. But you must satisfy these constraints, and you want to maximize a certain function. That's all a linear program is. You can take a whole class in studying just that kind of object. Questions so far on just the definition? Right? Yes?
How do you compare AX to B? Since they're a matrix, how do you know that they're less than B?
Some of this is sloppy, and not because I'm sloppy, but because everyone else is also sloppy. I'm not taking the fall on this one. That is component-wise comparison, right?
So if one component is larger, then the whole thing is...
Correct. Every constraint, all of them must be satisfied. It's an and in some sense of them, right? Yes. More questions? So, a lot of problems can be expressed as linear programs. I'll give you 3. The first one is going to be flow. So, max flow problems. Oops. Every max flow problem, given a flow network, you wish to express it. What is the max flow, right? You have a flow network. There's a set of edges that have a flow that can be assigned to those edges, and it must be between 0 and the hard-coded capacity of that edge, right? So we can, in fact, create a set of constraints and an objective function that has a solution which is exactly the maximum flow of any flow network, right? If I wanted to, what would the objective function be of a linear program? Max what? How would I write that? That's correct, exactly. I want the maximum of all flows. You're almost there, you're almost there. Max, sum of what? I'll just tell you, outgoing of S. What's the max flows of things that are outgoing from S? Let the variables instead of X, let them be the F's, and let C's be our constants, right? We want to maximize the outgoing flow of S. right? And so we let f of SU mean you're going from S to U for all U, if there's an edge there. Now, if there's no edge there, then that's not a variable. But you only do that for the variables, right? So what's the maximum flow outgoing of S? Equivalently, I could have said the maximum flow incoming to T. And as long as I set up my other constraints, those are going to be equal. Now, my other constraints are what? What are the other properties in a flow network? Does anyone remember? First off, we need this constraint. So if UV in E, we add a constraint of the form f of UV is less than or equal to C of UV, right? So this is going to be an element in A, and this is going to be one of the components of the vector B, right? The B, in some sense, is the coefficients. B is going to be the right-hand side. That handles the fact that the flow will not exceed the capacity, right? There's one more important part of a flow network, yes?
The flow in and out of any vertex has to be the same.
Exactly. Conservation of flow into any vertex and out of any vertex is equal, right? So what I could do is, let me first not write this like the standard form of a linear program. Let me just write this in the way we know, and then we'll try to translate it, right? So we want the sum for any fixed vertex, let's say V. We want the sum of incoming to V, so for all U. We want f of incoming, which is u comma v, to equal the sum of the outgoing. So for all u, f of v comma u, right? The sum of the incoming is equal to the sum of the outgoing. That's not a linear program for several reasons. First off, you can't have equality. You can only have inequality. You cannot have things on the right-hand side that are variables as well. You can only have constants on the right-hand side. So how do we fix this? Yeah. We subtract it from both sides, and then we set this equal to what? 0. Okay, one other problem, there's an equality here. How do we fix that? We want it's possible we want it to be equal to 0, because that's exactly what the flow requires. But the specification of as syntactically defined, a linear program only allows inequalities. Exactly. So how would you do that? Yeah, so I'll write it over here. You can say, if you want to write A equals B, what you can do, you can say A minus B is less than or equal to 0, and B minus A is less than or equal to 0. If both those are true, then it must be the case that A equals B, right? So you would simulate this with two different equations. And then, so just suppose I did that, right? And then finally, you would also have f of u comma v. For all, if u comma v is in E, you would have this to be greater than or equal to 0, right? Those are a simple set of equations that is a linear program that has a solution when the flow, every solution to these constraints corresponds exactly and precisely to a flow, and the max flow corresponds to a maximum solution according to whatever this objective function is. All right? This is called the objective function. These are the constraints, right? So again, and the spirit is, at least for this first part, is like, we're going to make many different problems seem like a linear program, and therefore, if you were to take an off-the-shelf linear program solver, it could just solve all these problems at the same time, right? So we talked about a specific algorithm for max flow. It was Ford-Fulkerson. There's other ones, but Ford-Fulkerson will solve flow. But if you have a linear program solver, it'll also tell you the flow, right? Will it be better? I actually don't think so, but that's okay. At least it solves many things at once. Questions on this flow example? Okay. What about Knapsack? Recall what was the in the search version of Knapsack? What were we seeking? We have a set of values. Wow. We have V1 to Vn, let's say, and W1 to Wn. Each set of values and set of weights, and we sought to steal as much as possible without going over a certain weight capacity, right? What would our objective function be? First off, what would our variables be? Yeah.
We consider variables are just x1 to xn.
Okay. And what should x1 mean, for example?
If x1 is 1, then we take item v1. Otherwise, and if it's 0, we don't take it.
Yeah, exactly. We'll have some more constraints to ensure that's exactly what x1 should be. For example, we don't want x1 to be 2 or 7, for example, right? If we're doing 0, 1 knapsack. So let max of, what should our objective function therefore be?
The product for each of each x and the corresponding v.
Yes, where xi is a 0 or 1, meaning we steal item I or we don't steal item I. If we steal item I, we earn vi. If we don't steal item I, then we don't earn vi. So some of those are going to be zeroed out, some of those are going to be added to our sum, right? That's our objective function. What are our constraints?
Sum of W's is less than half of them.
In fact, we have one constraint. What goes here?
The sum of the weights.
Yes, but what weights? The weights of the items that we steal, right?
WIX.
It would be wixi. To make sure it's exactly the ones that we steal. What goes here?
Big W.
Big W. So in some sense, Knapsack is a special case of linear programming when you have one constraint. Now, how do we ensure that xi is as we say it is? Well, honestly, we can't. So what we can do is just say, like, let for each I, let xi be less than 1. And by default, it's already greater than 0. Right? So how do we ensure, for example, xi is not 0.7? We can't. So as we defined, linear programs are not integer linear programs. We cannot specify xi can be 0 or 1. There's nothing we can do to prevent xi being 0.5. That's okay. It's still enough to show you an example. Remember we talked about ILP being NP complete, right? The reduction was, in fact, from Knapsack. But well, sorry, it was not from Knapsack, but it was, I think we did SAT, if I recall. But either way, ILP being NP complete, this is not ILP. This is specifically LP, linear programming. We'll talk about the differences later today. But either way, the language of linear constraints is, I don't want you to think that linear constraints are somehow a special case or something that's not very powerful. And like, oh, I want squares and square roots and stuff. I want to demonstrate that linear constraints are incredibly expressive. And basically everything that you could seek to do could, in an important sense, could be done in a linear way, right? Questions on that example? Okay, let's do, and this is a surprising one, we can do shortest paths, right? So recall what, in every graph problem, basically every time we computed shortest path problems, we did Dijkstra's and Bellman-Ford and even Floyd-Warshall, they all kind of relied on a simple constraint, right? Over and over. It was the fact that the shortest path through to a vertex was what? Let's see. It was dist u, for example, is equal to the min of dist u or dist v plus LUV, right? When there was an edge, let's say that right, you're computing a single source shortest path problem, let's say. You want to find the shortest distance to u. You can either first check what the distance is to some v, and then see if that gets you an edge, or the current shortest distance to u, right? So this is dist u, this is dist v, and this is LUV, right? So iterating over the graph in that way will, in the right way, in fact, will get you the shortest path, single source shortest path problem for every s. Is this coming back to us, remembering this, right? This is linear. That's a sum. There's no squares or square roots. So in fact, we can represent this whole thing as a linear program, right? So for each v, we could have the constraint, let dv be the shortest current path from S to that specific vertex, right? So we would want, for example, ds to be 0, because that's the shortest path from S to S is itself, right? But let's suppose we wanted something else. What kind of constraint could I give on du for some u, let's say? If we have an edge of LUV, then we know that whatever dis u is has to be less than whatever dv is plus this value, which is some constant, right? So we know that the distance to u is less than whatever that happens to be, right? So given a linear constraint like this, we can actually find the shortest path problem, right? But then here's the problem. Let's suppose we're not trying to find single source shortest paths through all vertices, from one source to one sink. Let's suppose we'll find the shortest path specifically from S to specifically to T, right? Then we seek to find a certain value, what? It's dt. I mean, that was just checking, are we awake? dt is going to be the value that we seek. But what about dt? Are we seeking to maximize it or minimize it? I got you guys, because I also fell for this when I was learning this. You would think you're looking for the smallest dt that this is a solution for. But unfortunately, the way the constraints are set up, this is actually what looking for a maximum. There's always a minimum solution dt that way, which is just dt is 0. But the only case where all the constraints actually simulate the way the edges work is when we choose to maximize this, right? The max solution to dt is the only feasible solution that actually corresponds to a path through the graph. If you have a smaller dt, that's actually something that's not a path at all. That's just like something malformed, right? So the max solution here is, we actually seek to maximize here. Sometimes a linear program can be, in terms of minimization instead of maximization, doesn't really matter. You can do them. You can just minus sign everything, right? So the fact that this is a maxing, the shortest path is actually the max dt subject to all these constraints, right? Any other solution to dt that's larger than this value will either not satisfy certain constraints or not be a valid path. So we seek to maximize here. It's not imperative or incredibly important that you understand that trick, but just know that we can express shortest path problems as a linear program. Again, the expressive power of linear programs, right? Questions so far? Okay, I want to talk two more things about, there are two important features geometrically that linear programs have that will enable an algorithm to solve them, I won't say efficiently, but it'll solve them. The first is kind of geometry-wise, right? Linear algebra is not the study of matrices. It's the study of geometry. And people kind of forget that when they're getting lost in the sauce, because there's all these other annoying things. Eigenvalues and eigenvectors aren't made up. They actually correspond to real things, but people forget it. So if I were to take the specific linear program that I gave prior, and I were to plot it, let's describe what those equations would look like, right? Forget the fact that they're inequalities. We can just consider them to be equalities for a second and then denote the inequalities. Let's suppose we plot x1 over here and x2 over here, right? Given the constraints of the first problem, what does it mean when we say that x1 is less than or equal to 200? How would I represent that?
Draw a vertical line at 200.
Great. Let me do it better. Hold on. Sorry, what?
A little to the left, because we'll need 400 later.
Okay, thank you. Now, this is when x1 is equal to 200. So if x1 is less than or equal to 200, yeah. Anything over there satisfies x1 is less than or equal to 200. Okay? What about x2 is less than or equal to 300? Right? And because it's an inequality, it's whatever is below this line, right? So What about, okay, now here's a tough one. How do you draw x1 plus x2 is less than equal to 400? How do you know how to draw the slope and everything?
Slope is negative 1.
There's some y equals mx plus b in there. There's an easier way. Intercept, yeah. Set x1 to be 0, and then figure out where it intercepts both xi, and then just draw a linear line between them. So x1 plus x2 is less than equal to 400. That means x1 and x2 themselves are at most 400. So we saw x1 is going to be 400. It's going to be like here, and then 400 is like, that's 200. So let's just, that's probably 400, right? So then I'm going to go like this. That looks right? Believe me? Okay. Okay. And this is x1 plus x2 is less than equal to 400, right? Now, if a linear program has a solution, the pair of points must satisfy these three inequalities. So geometrically, it must be within this region. Okay? Why is it above the y-axis and to the left, to the right of the y-axis and above the x-axis?
They're necessarily positive values.
Yes. Okay. So, when you have a linear program, one way to think of it is as a polytope. Now, this is harder to picture when you're in n dimensions, but a set of linear constraints actually corresponds to some sort of, a polytope is just a big fancy word for polygon. In the two-dimensional case, it's a polygon. We have some sort of shape, okay? And we seek a solution. The only possible solutions are in the region of the polygon, okay? But we seek a solution which maximizes some objective function, right? The objective function is also linear. So we can actually plot the objective function, but note that there's no intercept necessarily. It's some moving line. We seek some, and when you plot a line somewhere, like if you have something like that, every value on the line is equivalent, right? That's like the definition. There's some, we recall that? We believe that? If I give you a line, a slope and an intercept, and a x, y equals mx plus b, I give you all those numbers. Every point on that line will evaluate to the same objective function, right? That's the, okay. So no matter where I move that line, it only matters where I move that line then. So we seek a place that that line intersects, we seek an intersection of that line with the polygon to maximize that, right? So if this was my polygon, for example, I could be considering lines of there, and then I can move that up and down to consider where that would maximize it, right? But if you just, in pure guess, no, just geometric intuition, where should that maximization occur? Yeah, in a more polygonal wording. Near an edge? It's not going to occur, first off, it's not going to happen in the middle. Okay, what I'm trying to say, it's always going to happen at an exterior point. So a solution to a linear program always occurs at an extremal point. Why? Could it be, it's always at 1 point. What if it's 2 points? Why is it never 2 points? Or when is it 2 points? When they're equal, okay, but then what does that mean? Here's another question. Okay, suppose there are two solutions that are equal. Geometrically, what goes wrong, and how does that correspond to the linear program?
The objective function and plot it, then both the points will be there.
Yeah, so if there's two solutions that are maximal, that they're equal for, in fact, every point on the line is equal to that. So in fact, the objective function is then parallel to one of the constraints. So in fact, if these 2 points were, for example, a solution, then so would every point on this line. So then there'd be, in fact, infinitely many solutions and not just 2. So because we hope it would be a disastrous problem if an objective function was parallel to one of the constraints, that doesn't make any sense, right? It's always going to be usually 1 point, right? But what property of the polygon ensures that?
Yeah, edges are lines.
So the two portions, first off is linearity. So let's consider the fact if we were considering nonlinear problems. Let's suppose we had feasible regions which were nonlinear, right? We could have a quadratic of some form, linear, 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 okay? Let's suppose that was our region. And let's suppose our line was like this, okay? As we seek to maximize or minimize this, however this parallel gets parallel, it's going to be some point there. But if we're doing computation in the real sense, it's going to. How would we find that intercept? We would find where this curve intercepts with that point, right? But how do I word this? That's really hard to do. Here, the algorithm that will solve linear programming is called simplex. Excuse me. And it relies heavily on geometry, a geometric interpretation. Essentially what it's going to do is iterate upon external points of the polygon. But if you have to do something like this, I mean, this is disastrous. You could do a bunch of bouncing back and forth forever. It could take you a billion steps. So to some sense, nonlinear programming is either impossible or very, very difficult. We only get such nice guarantees from the fact that we're working in the linear sense, right? That's the first problem, and working with nonlinear things. I guess the other thing I was trying to hint towards is that if you have any set of equations, then the intersection, which is their feasible region, must always be convex. We hear the term convex in any context? In what context? Yeah, I get it. What is a shape not convex, let's say?
When you can draw a line between 2 points that exits the shape and comes back in.
Yes, exactly. A shape, a function, is considered convex if there is not convex, if there exists 2 points in the interior of the shape, and the shortest distance between those two exits the shape. That's when a shape is not convex, right? So a shape that is convex always has a interior region which is convex. Sorry. A set of linear constraints always has an interior region which is convex. And that's another reason simplex, the algorithm we'll detail, works. It doesn't have to deal with any cases like this, right? It'll never be the case that it has to, I can't describe how the algorithm is going to fail on a case like this, but just believe me that sounds like it would work way worse than something like that, right? High-level geometry here. We're not doing details yet. We'll do that after the break. But if I were to ask you to prove why does the intersection of linear inequalities can create a convex interior region, how would you proceed? And let's suppose I asked you to prove, maybe not totally formally, but give me an explanation. Give me some intuition, if not a proof. Why must the intersection of linear constraints construct a convex region? Let's suppose in 2 dimensions it's going to be a polygon. In 3 dimensions it's going to be something faceted like a gem. In 4 dimensions, whatever, it's a polytope. Why is it always convex? Why does that never happen? It's good to build geometric intuition as well as we go into the next algorithm. So.
I mean, it doesn't explain much. You can just say because it's linear.
Yeah, I don't know about that one. Yeah?
Because you're like always cutting a line and picking one side. So when that happens, you can't make a non-convex shape.
I would say that's close enough. If I were to I think we have the intuition, but if I were to word it in a proof by contradiction, I would say, suppose to the contrary, somehow linear constraints made in non-convex shape, okay? That means that thing exists somehow, okay? So it looks perhaps like this. Perhaps, okay? There is some feasible region that is not convex. But this edge is defined by a linear constraint. This edge is defined by a linear constraint. But any point here does not satisfy that constraint, and any point here does not satisfy that constraint. And because all constraints must be satisfied, it is not the case that this exists, but rather this exists. Contradiction. If there is a non-convex thing in there, no, there wasn't actually, QED. So it must be convex. Now, geometrically, you can think if you have an apple or whatever, and you're taking slices of it, and as long as the slices are always straight, you're always going to get a convex shape. You're faceting it, right? Intuitively, keep that intuition as we get to the next thing. Yeah, suppose we started with something convex. Suppose we started with something convex, and we iterate over it.
Start with an orange.
An orange is convex, yes. Okay. Okay, so this is, the first part is that the simplex algorithm is going to rely on this interpretation of geometry. One final thing is, there are situations where a linear program has no solution, and they all fall into two cases. But if you had to guess, when does a linear program have no solution?
When your shape,
Sorry?
when your shape goes away, and there's no more area.
If you have a shape of area 0, that would be considered not convex. Let's suppose you have, let's suppose it's not the case you have 0 equations. Let's suppose you have several equations. When does such a shape have area 0?
They don't have any overlap.
Yeah, so I could say x plus y, x1 plus x2 is less than or equal to 10. And then x1 plus x2 is also greater than or equal to 20. Right? Such a thing is called infeasible. There is no region that shares them. It could be the case that, for example, I'm shading this way and then also shading that way. There's no set of points that satisfies both of those. It's anything where there's no point in all of them, right? So sometimes the classic examples are like this. Right? And let the lines be that's the side that's shaded. So sometimes you have an infeasible linear program, right? There is no solution that satisfies both of these. Fine. There's another time the linear program does not have a solution. It's what? Let that solution be the solution. That certainly has a solution, as long as it's not infeasible. Yes?
Could it be our case where the objective function is parallel to one of the constraints?
In practice, we would say we don't like when that happens, but we allow it. We're like, fine, you can have a solution. I guess what I mean is that would be, we would call those solutions, but infinitely many so. Yeah.
Like feasible region isn't bounded.
Yeah, unbounded. So consider max x1 subject to x1 is greater than or equal to 0. So I'm just, send it, right? There's no solution here. This is called unbounded. Right? If I were to draw a set of equations that satisfy this, maybe it's like, right, you can always choose farther and farther points to maximize whatever your objective function is. Yeah, if you want it in the two-dimensional situation, if you want to consider that way, yes. The volume of the polytope is infinite, so there is no polytope. It cuts off space in one side but not the other. Okay. We will come back to why infeasible and unbounded linear programs are, like, in details. How do they work? We'll talk about that later. Questions on these so far? Okay, so another important thing about the fact that everything is linear is that the algorithm, conceptually at least, is quite simple. There are actually several algorithms that solve linear programming, and again, you could spend your whole life on them. Some of them, the simplex algorithm is the simplest one. And all the simplex algorithm does is it is a greedy algorithm. And it's allowed to be greedy because the objective function is linear. So if you were to guess how to find, how to maximize an objective function, All you have to do is like try a value, and then if that one's bigger, then that's your new solution. Just repeatedly try a small value. We know by convexity arguments that the optimal solution, if it exists, is on the exterior of the polytope, right? So what we can think about is simply, let's say we have something like this. This is our, no, that's not convex. Okay, something like that. All the simplex algorithm does is, in a geometric sense, I mean, we'll describe how it does in detail, take the exterior of the polytope, start somewhere, maybe 0, 0, and look at the neighbors on the polytope. Traverse to any neighbor that increases the objective function, and repeatedly do that until you can't anymore. So the simplex algorithm really, in some sense, is a walk along the polytope until we find our maximum. That's all it is. Yes?
What's the point of looking at non-edges?
What's the point of looking at non-edges?
If you only consider the edges of the polytope?
Yes.
Every one along the way, every point along the
He
way.
drew a 3D shape, they're all edges.
Oh, I'm sorry. This is yeah, the board is two-dimensional, but
Yeah, okay.
sorry, what was, pretend this is a gem in 3 dimensions, like a rock, okay? We're walking on the exterior of a rock, right? In the polygonal case, it's actually easy, because in 2D, you can only turn left or right. But in 3 dimensions, you have a set of choices perhaps you could make, right? For example, if you are, let's suppose you have, a function in 2 equations is a line, a function in 3, a function in 2 variables is a line, a function in 3 variables is a plane, right? So if you had a single variable, you could have 3 intercepts, and that would denote some kind of triangle thing, right? Picturing it, right? So when you're at this point, you have 3 choices to make. Something like this. All the simplex algorithm it does is, I mean, this is it. To give you more detail, I could write it at a high level like this. Begin at a 0, 0. While true, if for any v neighbor of v more optimal, set v to the neighbor. Else break. Of course, that's not how simplex is actually implemented. There's a bunch of linear algebra, which we'll do soon. But that's conceptually and geometrically what's going on, right? Simplex is a greedy algorithm in the sense that, oh, there's a solution that's next to me that's better. That's my solution. Oh, there's a solution that's next to me that's better. Okay, that's my solution. Oh, I don't have any more, there's nothing better than me that's next to me. Done. In some sense, if you have like a prior experience in differential equations, you could think of there's like a linear gradient field, which just kind of like pushes you along the polytope to the right place. You know, you're always going to be swimming uphill. And it doesn't even matter that you choose the maximal of your neighbors. You just choose, as long as you're choosing a better neighbor than yourself, you're eventually going to end up at the right spot, right? Now, how does this actually work? What is a point in a polytope in the linear sense? Like if we have a linear program, what is a point? Yeah, so a point is when 2 lines intersect, right? That's like Euclid and stuff, right? So a point is in some sense when 2 lines intersect. So if we were to think in terms of the constraints, what does that symbolize? Yeah, these are 2 constraints, and you are at the edge of both at the same time. What that means is both those constraints are what we would call tight. Those are not inequalities at that value that you're currently at, but they're in fact equalities. So you're in fact at the summit of those 2. The way the translation works from along the interior point is you do this relaxation tightening game, where to cast yourself away from this point and go to this point, you say, I'm going to loosen this inequality to tighten another. and you repeatedly loosen and tighten inequalities until you reach optimal. That's kind of, we'll explain how that works in the math in a second. But before that, we'll do a very simple example. Any questions on this? Okay, let's go through a quick, simple linear program. Suppose I wanted to max 2x1 plus 5x2, subject to, let's say 2x1 minus x2 is less than or equal to 4. X1 plus x2 is, 2x2 is less than or equal to 9. Minus x1 plus x2 is less than or equal to 3. And x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Suppose this is our linear program. A quick way to do it is just to consider when are two, this is going to be a polygon and not a polytope or something because we only have two variables, x1 and x2. We know that we're in the first quadrant because x1 and x2 are greater than or equal to 0. If we were to consider quickly how would you determine quickly when when are two constraints tight? Yeah.
Replace the inequalities with equalities and then solve them for the variables.
How would you solve them?
Probably using the methods we learned back in middle school about how to solve systems of linear equations.
Yeah, you can do matrices. It's probably a determinant trick, plug and chug, Gaussian elimination, whatever. Who cares? I'll just tell you what the answers are so we can make things simple. There's an intercept here at 0, 3. There's an intercept here at 1, 4. There's an intercept here. Let's see. At 2, 0. And then there's a thing here at like 3.4-ish, 2.8-ish. Okay, pretend that's straight lines. That's our feasible region, and we start at 0, 0. So we plug in 0, 0 into the objective function. What should we get? Okay, now we have two choices to make. We can either go up or we can go to the right. So that's a problem when you consider two dimensions. It's actually kind of too easy because you always know you're going forward or backwards, right? You're going around the loop or clockwise or counterclockwise. So if we plug in 2, 0 into the objective function, what is the value here? Y. 2 times 2 plus 5 times 0 is 4. So this is 4. Okay, fine. What about that one? 15. 2 times 0 plus 3 times 5 is 15. So this is 15. So 15 is more optimal than 4. Now it's not necessarily true that the simplex is implemented that you take the max of the neighbors. Just as long as you take a increasing neighbor, you'll eventually get to your maximum. Why that is, we'll talk about that later, but this happens, right? But let's just suppose we did take the maximum. So let's go to 0, 3. So what we're going to do is leave this point and end up on this point, okay? Now, of course, we're not going to go backwards, so that makes the two-dimensional case kind of too simple. But if we were to consider the next point into the objective function, what would that be? Yeah, 4 times 5 is 20 plus 1 times 2 is 2, so that's 22. Okay? 22 is more than 15, so we're going to go there. 3.4 and 2.8. That's tough. Does it? Well, tell me the number. Also, it's not even exactly 3.4. There's some other decimal there. It's
20.8.
yeah. If you wanted to actually tell me what those numbers are, I don't care enough. It's 20.8-ish, right? But we're currently having an objective function value of 22. So if we were to move to 20.8, we would actually decrease. So we stop. We don't go there, and we say, oh, all right, we found our maximum. Now correspond this to the linear program. Let's see what happens. This corresponds to x1 equaling 1 and x4 equaling 4. Oh, no, x2 equaling 4. And that corresponds in the word problem to whatever this linear program is supposed to be. You produce this much of this item or that much of that item or whatever, right? So which constraints are tight? Which ones are not? Let's plug in x1 and x2 in here. What's our left-hand side?
Negative.
Yeah, so we get, just to quickly show you, negative 2 is equal to 4. What is this one?
9. That's tight.
9, yeah. So we get 9 less than equal to 9, okay?
That's also tight.
Sorry, what?
That's also tight.
What is that, 1 minus 1 plus 4 is 3? Yeah. So you get 3 is less than equal to 3, right? So notice that this equation and this equation are tight, but this one isn't, right? And the sense that it's tight is that you cannot make them more maximal. But these two equations are exactly what? They're exactly this line here and this line here. And you being at that point corresponds to exactly that solution. So that equation that's not tight is in fact this exact line, right? So this is just the high level, really sketchy geometric part of linear programming. We'll get into the meaty, greedy stuff after the break. But before that, any questions on the geometry, on the intuition behind simplex before we actually do matrices? Okay, let's take a break.